Okay, I think we can start. Hello, everyone, and welcome to this Rubin assembly. This is the first one of our science preparation special seminars, and today we're going to be talking about dark energy and cosmology. My name is Andres Plazas Malagon, and I will be co-hosting this assembly with my colleague Shen-Ming Fu. We both work at the SLAC National Accelerator Laboratory, and we are part of the Rubin Observatory's community science team. As usual, this is our agenda. We're going to start with some quick announcements. We're going to talk a little bit about the cosmology that you can accomplish with the LSST data. We want to highlight and make an emphasis on the data products that will be relevant for cosmology with LSST. And then we'll conduct a data access demo with the notebook aspect of the RSP and show as well some screenshots about the portal aspect of the RSP relevant to access those data products. And then we'll have some time for Q&A, questions and answers. So announcements, an important announcement is that the registration is open for the Rubin Community Workshop 2025. This is going to happen in Tucson at the end of July, the beginning of August. It's going to be there is a post on community and there is another important announcement is that the LSST camera has been installed on the telescope. There was a press release by the NSF and the DOE. So check that out. There's a lot of cool pictures and it's building excitement now that things are getting closer and closer. The next Rubin assembly will be next Thursday, continuing with this series of seminars. It will be focused on strong lensing. More generally, the Rubin assemblies scales has moved to rubinobservatory.org. The assemblies will still be announced in community and in the LSST Discovery Alliance Slack space. And as I mentioned, today we're going to be talking about dark energy. The next week we're going to be talking about the strong lensing, and there are other assemblies related to the LSST science pillar. So please keep an eye on those, and we hope to have you attend as well. I wanted to also promote the Link frameworks office hours. The Link frameworks has a mission to enable scientists to develop scalable and productionized software algorithms in collaboration with the broader community. So they do have a series of office hours and also sometimes talks alternating in between weeks right after our Rubin assemblies. So please take a look. There are very interesting projects in which the Link frameworks have collaborated with. I wanted to highlight the Rail frameworks for photometric redshifts for the mission of dark energy in LSST. I also wanted to remind you that we have a users committee within Rubin, and it is charged with soliciting feedback from the community. You are the community about the data products from Rubin and the Rubin Science Platform. They do recommend improvements to the project twice a year in reports. There are links here where you can find more details about their charge, but in particular, there is an email address where you can contact them, or you can also use the community forum in order to contact them. You can find the members of the committee listed in this slide at the bottom, and I'm pretty sure you will recognize many experts of different areas, scientific areas that will be relevant for the LSST. So please don't hesitate to get in touch with the users committee to get your feedback about the Rubin data products and the Rubin Science Platform in general. If you are new to these assemblies, welcome. And if you have data rights, you are welcome to just get a Rubin Science Platform. It's very easy. And if you don't know if you have data rights, you can contact us. But in a nutshell, is if you're doing research in astronomy in the United States and in Chile, there's also a list of international partners that we can help you identify that if you don't know that. Right now, we have simulated data, which is what we call the DB0 data simulations. One data set for extragalactic and galactic objects, and one for solar system objects. The extragalactic simulation is called DB0.2, and the demonstration that we will be giving today will be based on those simulated data. But as you know, we already did some commissioning with the commissioning camera, so And we are also getting ready to get the survey started. So we'll be having on sky data release hopefully very soon. Please check out the For Scientists section of the relatively new rubinobservatory.org website, and with lots of important information. Today, we're going to have, as I mentioned, a demonstration of a tutorial in the notebook aspect of the Rubin Science platform. If you have an account, you can go to the usual website, data.lsst.cloud. Then you can click in the notebook aspect of the website. You will see the three aspects: the portal, the notebook, and the API. And then briefly, you will be prompted to choose an image and a size of the server, something like this actually. So you just click on recommended medium, and then you can clone this GitHub repo, which is github.com/rubindp0/dp1 sci-prep seminars. And then you will find the notebook that we're going to talk about here today in there, if you want to follow along. But I will be sharing my screen and we'll be going all together through that. Next, Shenming will tell us a little bit about the cosmology that you can accomplish with the LSST. So, Shenming.
Yeah, thank you. Yeah, this should mean so briefly talk about the cosmology and SST. Could you go to the next slide? Yeah, so caught in the current theory, the universe start from the Big Bang, then inflation, so the quantum fluctuation in the original universe, they would be amplified. Then that's the fluctuation we see in the CMB, the cosmological microwave background. And then there's the dark age, and then the stars form through the gravity, the fluctuations in the cosmic microwave background will be amplified. And then stars and galaxies and galaxy clusters, large scale structure gradually form. And nowadays, the portion of dark energy becomes much larger. Then we have this new phase called accelerated expansion. So on top right, that's the current mostly used model for the universe. So about 5% we call atom, but basically those are the normal matter, the regular matter, the things we know. So basically the bottom right, those are the standard model for the particle physics. We know those particles. But about a quarter of the universe, those are dark matter. So they have mass, they have the gravity, but they don't have, or may say, very weak interaction with other like forces. Then dark energy, about 70% is dark energy. So it's like an energy. Um, but the question is, dark matter, dark energy, they just cover a very large portion of the universe, but until today, still we don't know what they really are. So this also the thing we want to investigate using LSST. Could you go to the next slide? Um, so in this slide, basically, I listed a few like techniques or approaches. We study the cosmology using LSST data. The first set will be the geometry of the universe. So what we like to measure the distance of the universe and compare the distance of some object and compare that with the redshift. So basically the angular diameter distance, we could use standard ruler, the BAO, the baryon acoustic oscillation, and strong lensing. And then luminosity distance is another type of distance. We can use standard candle like type 1A supernovae. The second set is the matter in the universe, like how much there are in the universe. So we could use the power spectrum. So basically we use the weak lensing, cosmic shear to achieve that. And the third group is the growth of the structure. So for example, the mass function of halos. So that will be galaxy clusters. And there are also other combinations, other probes. Those are just examples. and also like joint analysis. For example, 3 times 2 cross correlation. This is pretty popular nowadays. Shear density, and shear density correlations. So that include both cosmic shear and clustering information. Could you go to the next slide?
Okay, that's me. So within the LSST, we have 8 science collaborations. One of them is a collaboration focused on dark energy, which is the Dark Energy Science Collaboration. If you want to do cosmology with the LSST, you don't have to join a science collaboration, but we encourage you to do so. And the scientific aim of the Dark Energy Science Collaboration is exploring the physics of the dark universe. It has the dark energy at its core to figure out the nature of dark energy. As Ming said, there's also other objectives, such as studying dark matter. We also want to study neutrinos and their signatures and other signatures of inflation. So we have 5 cosmological proofs, at least. Shenmin mentioned some of them. We have clusters of galaxies, the large-scale structure of the universe, supernovae, weak lensing, and strong lensing. So please, you can use this QR code or visit the lsstdesk.org website in order to become a member. Again, if you have data rights, you are welcome to join the desk. And there is a large participation between the members of the desk and the Rubin Observatory. So there is the Rubin Observatory is managed jointly by the NSF and the DOE, by NOIR Lab and the SLAC National Lab. The desk has SLAC as its national laboratory, host national laboratory. And if you join the desk, you will find that you have other resources available to yourself, such as the NERSC supercomputing environment. There's a lot of feedback between members of the desk and members of Rubin. So yeah, that's also another opportunity also to get involved also with the Rubin and desk as well. And just to give you a glimpse of what it wants to be achieved, if we look at the desk science requirements document, here you will see that the improvement that is expected to be achieved. So what is shown in these 2 plots, there are forecast plots in which we have a particular parameterization of the dark energy. Dark energy usually we parameterize by a variable called W, which is the ratio of the pressure of the energy density, and this is the equation of state parameter. The fiducial values so far, data are consistent with dark energy being a cosmological constant, in which case that W is -1. And then we also are very interested in asking the question, does dark energy change with time or not? So that would be that W sub A parameter that you find as well. And especially, so these figures are actually characterizing the size of the error bars that are the reduction in the error bars that will be accomplished once the LSST 10 years are done. And this is very exciting, actually, particularly in this week. If you've been following the news, we have results from the Dark Energy Survey, DESI, other 80 Atacama Cosmology telescopes, and this is a very exciting moment to be in cosmology because there are some hints to that dark energy might not be constant in time. So the LSST will give us the answer. But now we want to focus on the data products that you can use in order to do cosmology with Rubin and with the LSST. So Shenming will tell us about this.
Okay, thank you. This is the first slide for data products. At top, there's a link for the planned data product. So you can see from the title, things might evolve. So things could change. So just keep following what data product will be provided. But here, I want to point out some essential pipeline steps and the related data products will be useful for cosmology. And here, we are focusing on static science. Of course, time domain science also would be able to do cosmology like type 1 supernovae, but those topics will be covered in a future session. So the first thing is coaddition. The images will be stacked every year, those annual stacks, and then they would make this deep coad. This is the name for the coad images. Then the images themselves is also very useful because, for example, strong lensing, if you want to look at strong lensing features, strong lensing system, we can directly check those system in the images. But for other science, we want to do some measurement on the images. So first, the detection on the co-ed images, then do deep blending, then we have the objects. Objects means something repeatedly show up in the exposure. Per exposure, that's sources, but on the acquired image, we call that object. Then we have the object table listing the quantities and properties of those objects. Then there's the co-ed measurement. For us, for the cosmology, the most important thing is we want to learn the lensing shapes. So in the future, there's going to be a table called a shear object table, and that's related to an idea about the cell-based co-ed. The cell-based co-ed, just in brief, that's basically the co-ed of images in small cells, small area on the sky. And then this is to make sure uh, uh, the PSF in the co-ed. Then shear object table would do some shear measurement, mainly meta detection, meta call on those cell-based co-ed. And the last one is there's a co-ed for photometry. So if we fix the measurement at different bands, we can get a very good, accurate color information for the object. Then that's very useful for photometric redshift measurement. Could you go to the next slide? Okay, so earlier science data. I mentioned this before. Currently, we are using something called DP0 data preview. There, so
The sound is
that's
not good.
mainly the simulation data. So that's from the DC2, the data chains 2 from desktop. Yeah, sorry, my internet might not be very stable.
Yeah,
Then
Shannon,
that's
you're
the
cutting in and
DP1.
out a little
DP1 is
bit.
the,
You're just
yeah.
cutting in and out a bit. Just maybe try to talk a bit slower.
Oh, sorry. Let me just be slower.
Maybe you can turn off your video if you want for a second.
Right. Yeah, let me turn off my video. Okay, so let me talk about the DP1. DP1 is the commissioning camera, the ComCam data. The data has been collected and it's been processed. And then the next one will be the DP2 data. That's using the LSST camera, the LST cam, and that's for the science validation. So that will be 100 square degree on the sky, and that's at the 10-year depths, 10-year LST survey depths in 6 bands, UGRIZY, plus 1,000 square degree. That's only 1-year depths, and in GRIZ 4 bands. There's a techno, you can check more details there for the DP2 data. And then after DP2, that will be the LCT survey data. DR1 will be the first 6 months. Then there will be like DR2, DR3, and following every year. I can give more details in the next slide. Could you go to the next slide? Okay, so in this table, first, those are the early science data products. You can find this table in this file called RTN11. Also, I also would like to point out, since evolving, so the table might be updated in the future. So here I use the blue color to point out this the current data set we use a lot, this DP02 data, and that's the reprocessed DC2 survey data. The the things available, raw images, the processed vivid images, source catalogs, the coded images, object catalogs, and then some time domain catalogs, like force source and DIA, difference image catalogs. Then there's the one I mentioned earlier, the cell-based COAD and the shared object COAD. So shared object catalogs, those are not available in the current DP02. Then soon we will have this DP1 data. That's the ComCAN data. Again, it has raw images, the processed vivid images, source catalogs, the COAD images, object catalogs, and the cell-based COAD and the shared object catalog are not available. Then there's some time domain catalogs. They could be stretch goals, so they might be available, might be not. But from DP2, the cell-based COAD and the shared object catalog, they might be available. But after that, that DR1, DR2, DR3, all those shell-based COAD and share object catalog, they will be available. So that will be very helpful for the cosmology analysis. There's the last three rows in this table, the first, the source catalogs, the difference image DI catalogs, and SSP catalogs. SSP is for solar system. Those are all time domain related catalogs. So we will cover them in a future talk. So the basic idea is in the DP1, we will have something for analysis. And BP2, there will be more catalogs, but starting from DR1, we will have the full set of data products for analysis. Okay, could you go to the next slide? Yeah, so here is a list of like examples. Just this is not like a full example. This is just some user cases. We can use the data and use those data in some cosmological probes. The schema of the tables is in this link. And I mentioned earlier, share object is not available in DP1, maybe in DP2, but will be in DR1 and later. So the first probe, the weak lensing, usually we also call it the cosmic shear. It will need the object table. We need to know where the galaxies are, and then the photolith, the photometric redshift, and the shear object for the lensing analysis. And then BAO, baryonic acoustical oscillation, that's mainly for the clustering of galaxies. So we need the object table to know where the galaxies are. We need the photo Z to know the redshift. Then galaxy clusters, again, we need the object table to know the position of galaxies. We need a photometric redshift. We might need the shear object to understand the lensing effect. Then type 1 is supernovae. So that's mainly the time domain because they're transients. So we usually detect them in different images. So we need the DIA source catalog. We might need the photo Z if we want to know the redshift, but we might also use the SPECT, the spectroscopic redshift, to determine the redshift of the supernovae. Then strong lensing. Strong lensing, there are different studying cases, but first we need the object table to learn where the system is. Some strong lensing, they also looking at the time domain. So basically the time delay between the multiple images of the background source. So in that case, we needed the DIA source catalog. But we can also just look at the Einstein ring and do some analysis. Then we don't need the time domain information. The shared object catalog might be useful because we would know the shape of the system. And that can also help us to determine whether it's a real system or not. So things like that. But of course, there's some other user cases. Okay, could you go to the next slide?
Yes, thank you very much, Shenming.
Okay, go ahead.
Yeah, so now we're gonna demonstrate a little bit how to access these some of these data products. So we're gonna start with a notebook demonstration. As I mentioned before, you can go to data.lsst.cloud. We'll go to the notebook aspect of the RSP. So today we're going to mention specific cases about the use of point spread function modeling in weak lensing and also galaxy cluster lensing. I wanted to point out that this notebook that we're going to present today is a combination of other tutorial notebooks that are already available in the DP 0.2 set of tutorials that the CST has made available. We're gonna mainly use the object table, and we're gonna talk about again the PSF and Galaxy cluster lensing. So let me start sharing my notebook. And then after we're done with this, Shenming will also tell us about the portal aspect, and we'll have some time for questions as well. So I'm already here in the Rubin science platform. Let me just go back to the top. Let me get rid of this to have some more space, increase the size of the font, so maybe it's nicer to see. And then again, we have this standard acknowledgements that you find and information that you find in our CST tutorials. One nice thing that I wanted to point out is like, you will notice that here at the top, we have a tab that says tutorials, DP 0.2 or DP 0.3 if you want to do solar system, but you're here for cosmology. And in particular in DP 0.2, you can go to this one, 12B PSF science demo. So that's one of the tutorials. Yes, go ahead. That's one of the tutorials from which we're taking information for the tutorial of today. And the other tutorial is a new tutorial actually just merged this week by Shenming about cluster lensing. So you can easily access those tutorials, and you can see that there's a lot of very nice information here that you can go at your own pace. But in the interest of time, I'm not gonna go a lot into the details of what's going on, but I wanna focus on the access, the data products that we're using. So just, I'm gonna start with the PSF part, the point spread function part, and just as a motivation is that we're interested in using the weak lensing of the large scale structure of the universe that's called cosmic shear to learn about dark energy. But that signal usually comes blurred, or also comes with something called the point spread function, which is how a point source, like a star that is very far away, would look like in your detector. And point spread function modeling is a very fundamental part of a weak lensing analysis. And it arises from various factors such as atmospheric conditions, telescope optics, sensor effects, etc. So here I'm gonna show a little bit in section number 2 how to explore the PSF model measurements that you can find in the DP 0.2 object table, the objects detected from the deep coat. Then I'm going to show an example of what is called the chromatic dependence of the PSF, like how the PSF, the wavelength dependence of the PSF. And then in the end, I'm going to talk about something called the raw statistics, which is important to identify system axis in cosmic shear analysis. And then again, this is already in Science Demo 12B, and there's already a recording of myself presenting this a few months ago. But if you go to this tutorial, you'll find some reference to the literature. You don't need to understand everything in there in order to follow this. We do some standard imports of packages such as matplotlib, numpy, the feeder from scipy. In particular, we also import the table access protocol service that will be important to get the data. And we calculate the raw statistics via something called the analysis tools within the LSST science pipelines. So yeah, we start at the top, defining our tab service here, just very easy, one line. We get our table access protocol service. We define a standard for a colorblind friendly palette. And this is just a standard definition of a power law that we'll use in section number 3 about the PSF chromaticity. Okay, so the measure PSF properties in the catalogs, in particular the object catalog. We can start here. You can look at the, sorry, well, we got We got here our service here. One way in which you can actually look at what is actually in the browser in the object table is to look at the schema browser. We have a very handy website with all the schema browsers that you want, and then of course there's a lot of information, everything that you can think of. But it's, let's say you want to know only about PSF, you can just put PSF here in the search, and you will find everything related to PSF here. So this is one way of knowing what's in the object table. I didn't run this command here, but you can also have an example of doing it from the notebook itself, and then you can take a look at what's in there. In particular, for this exercise, we're interested in measurements of flux from PSF feeding, flux and flux error per photometric band. We all have also certain flags. We usually want to filter our data, for example, if the feed failed or not. If we want to calculate the shape of the size of the PSF model, we're going to have measurements of the second moments of the surface brightness, which are these IXX, IXY, IYY. And we have other particular quality flags. Well, this one in particular is called the inexact PSF center, but the one here above is a flag that tells us if the particular bright star was used for the PSF model or not, because not all bright stars are used for that. Okay, we select a point in the sky. It's a particular point in the sky that was used in a previous notebook for a particular band, in this case, just for examples, just for the sake of examples. And then we're gonna put some constraints on our query. So we're gonna have a flag that is called detect is primary, that is always recommended to avoid duplicates and unblended objects. We want bright objects with a flux larger than 360 nanojankies. And then these are the same flags that I mentioned before that are going to help us filter better the data. So this is the point where we get to the query. So it might look scary at first. The first time I looked at this kind of query, it's like, oh, but then if you just look, it's very intuitive actually. It's AstroSQL's query. So we're going to select the position. We're going to select the flux variables per band, the I band. Then the second moments here. And then we have some extra information that we're requesting here because we're going to use it when calculating the raw statistics, the correlation functions that I will talk about later. Some of the extra constraints that I already mentioned before. Then we have some magic to convert this to, in the end, to a pandas data frame. If you don't like pandas, you can convert it to something else. AstroPy, I think it returns a table, AstroPy table. So once it's run, it actually took like a little bit more than a minute. So I'm not running it in it right now, but it gives you an estimate of how long it took. You're always welcome to explore what you got in your objects result, that variable. So you could uncomment this kind of cell and then tell you what you got and confirm. We're not doing that right now. The first thing that we're doing is adding another quantity to this object table, which is the PSF size. And then we have a way of defining the size of the PSF called the trace size, the trace radius, which is just a linear combination of the two of the second moments of the surface brightness. So we go through some of the bands of interest, and then we define new table per band, just calculating that quantity for the size. That's going to be handy. We also get the coordinates here. And that's it. That's it for the part of preparation of getting the query and the data that we need from the object table via the tab service. Now, the first example is that we want to do is I wanted to show you the wavelength dependence of the scene. And this is also an important systematic in weak lensing because I mentioned that the weak lensing signal comes in the distortion of the galaxies of the shapes that also comes with a convolved point spread function. And in theory, you just get your PSF model. And then you deconvolve that PSF, and then that's it. It's not as easy as that. But that assumes, for example, that the spectral energy distribution of the stars is the same as the one as the galaxies, and that's not true. So there is usually a dependence of wavelengths on the PSF. One that dominates a lot is the one from seeing of the atmospheric contribution, which is predicted by turbulence theory called Mogorov theory to go this size of the kernel of theta of the seeing kernel is expected to go as lambda, as the wavelength to the minus or 1/5 or minus 0.2. So that's basically what we wanna measure. There are other contributions to chromaticity of the PSF, something called differential chromatic refraction or something from the CCDs. There's some literature here that you can take a look at, but let's look at actually at the calculation that we want to do also for the sake of time. So we define an array of wavelengths of the LSST filters taken from the LSST science books, the center wavelength. We calculate the mean size per band, these new quantities that we defined in the object table, and we calculate some error for the size as well. And then that's it. We have all that we need to in order to do this calculation. Then we just call the feeder from SciPy and then calculate, just do the fit in a grid. Then we get an amplitude for our power law, but then we get also an exponent, which is the one that we're also more interested in. And in this case, we got something, the absolute value of that exponent is 0.1.7, close to 0.17. You can say, well, that's close enough to 0.2, yes, but actually maybe not. That's not that close enough to 0.2. So it's not that serious here. Like after doing some digging with the experts that created the simulations, we find out that there's two things that might be going on also, that why this is not closer to 0.2. It has to do with the outer scale of turbulence being finite, but also something related to how the chromatic sensor effects are, some of the assumptions of that chromaticity of the CCDs were not correctly put into the simulations. And that might actually conspires to give us a result that is closer to what we got and not closer to 0.2. But that's fine in this case. You can read the details more in the document, or you can ask me more. But this is just an example of how you can calculate this type of quantity. So let's visualize it. So this is a power law. We have the mean size as a function of wavelength. We have the power law fit that we can say that maybe it's not the best fit, but then again, we're not completely concerned about that. It's just, it was nice to be able to detect an important systematic effect in the PSF. And then this next slide, next cell is just a different way of visualizing this power law, just overplotting the histogram of the sizes. So that's this section. The other section I wanted to talk about is the calculation of raw statistics, which are actually 2-point correlation functions that will tell you about how good your PSF modeling was or not, and it will help you about finding systematics in your weak lensing analysis. So is rho is the Greek letter rho, but it's also a play on words of the author that first proposed them, Barney Rowe, ROWE, in a paper, Rowe et al. 2010. But the point is that these are like 5 correlation functions that maybe you can look at the definition here very quickly, that have to do with these deltas in the ellipticity model and the measured ellipticities of the stars. And then these t's here as like fractional errors in the size of the PSF. So this is the kind of correlation functions that we are calculating. And every time you see a cosmic sheet analysis or a cosmology analysis from DES, or you will see from LSST, people will want to look at the accompanying paper which has systematic errors, and that will show this type of statistics in order to be able to trust the analysis that we made. So we're going to use a framework called analysis tools within the LSST science pipelines. And we're going to define, we need to do some preparation here in order to get to the calculation of these raw statistics. So these analysis tools underneath the hood are going to use a package, an external package called TreeCore, which is used usually in the community to calculate 2-point statistics. But you can also do that directly at the RSP. But here we're using the analysis tool to calculate the raw statistics. So for the sake of time, because I'm actually running out of time and we want to have time for questions, what's happening here is we're doing some selection of the data, some preparation of the parameters. You can access parameters of TreeCore via analysis tools. And then here you can look a little bit in the schema to see the type of quantities that you need to request in the original query in order for this to work. Then in this line is actually the raw statistics are actually being calculated. Once it's done, then you got a variable here, process results. You are able to access those correlation functions, the angular separations and the amplitude and the error of the correlation functions. So you can do whatever you want with those data, but also we have some plotting utilities here in analysis tools that will show us more or less what these correlation functions look like. So here, I guess you need to be a little bit of an expert in the field to see what you expect. But we can tell you that in this DC2 simulations, this is not like a super inhomogeneous PSF field, and we're not expecting something out of the ordinary. But you can play with finding these correlation functions in different bands, and then now you know how to calculate these type of things with actual data when the data will come. So there's nothing like super obvious to point out here. It's just that they're small, and then this is expected because it's a well-behaved simulation. Okay, I wanted to point out those two examples, and then maybe we can move to the cluster lensing part by Shenming.
Yeah, thank you, Andres. I just quickly go through this. Agilize clusters. I just want to point out two things. One Catalyst cluster, they have very large mass. So when we talk about cluster lensing, there could be strong lensing, like very strong lensing effect around the clusters. You might remember some images like strong lensing arcs or Einstein rings. But for weak lensing, if we go to very far away from the cluster, there's still weak lensing effect. The galaxy shapes of the background galaxy shapes, they're weakly distorted by lensing. It's difficult to tell the lensing effect, just look at the single galaxies, but we can use statistics to infer that lensing effect. And this is also related to the weak lensing, the cosmic shear topic Andreas just mentioned. We would assume if there's no lensing effect, then the galaxy shape on average will be zero, like random. But lensing effect can change that statistics. And we have to use statistics to learn that very small signal from lensing. And the big difference between the large scale structure lensing, the cosmic shear, and the cluster lensing is that cluster weak lensing is usually bigger than the weak lensing in the cosmic shear, about a magnitude higher, like about 10 times higher. So that's why the way we analyze that would be slightly different. Could you go down a little bit? So there's a known cluster in the simulation. So basically, we also use this TAP, this table access protocol, to get the catalog around that cluster. Yeah, could you go down? So here again, we use this get TAP service to first make service, and then we need to make query. In the query, there's some information we need. RA-DEC, those are the celestial coordinates. And then the C model, C model is a composite model magnitude. We use that for galaxy photometry. So we need R band, we need a G band, and so we need the shape measurement. Here we use R band shape measurement. There's a shape measurement called HSM. You can find more details in the reference. So basically, it's giving you a shape after the PSF correction. So it's trying to infer the original shape before the PSF. That's what we need for the lensing analysis. Then we make a cone search around the cluster, and then once we make sure the galaxies they have high quality, so it's primary. It's a primary object. It's had high quality, and the extendedness is it's like a flag telling you whether it's a galaxy or star. And then C model flags, we want to make sure the quality of the photometry is good. And also some other quality check like the PSF flux, the centroid flux, centroid position, and also some cut on the HSM shape, and also the blendedness. Make sure the galaxy has high quality. Could you go down? Yes. So some of those cuts are also from the previous papers. They use this HM shape. And here we make a query and then run the job. Then the job would finally return a table. Then we just check some details in the table. First, want to make sure the flux error is bigger than zero, just to remove those unphysical results. And then we want to make sure the signal noise is big enough. So 5 sigma is usually a value people would use to make cuts. So we make sure the signal noise is bigger than 5. Could you go down? Yeah, then we would like to do some analysis on the sorry, here is also some cuts on the utility. So make sure the utility is small. So because noise, there could be some big utility in the measurement. We want to remove them for our analysis. So after those cuts, we have a smaller table, and we want to do some analysis on that table. Could you go down? So here, the first thing to check is the rest sequence. So in the cluster, it's like a typical feature in the cluster. It can be used to detect clusters, can be used to get the cluster member galaxies. So we get the magnitude from the flux. Can you go down? Then we have this color magnitude diagram. So in this figure, you can see a concentration of galaxies at G minus R about 1. So those are the rest sequence galaxies. And this galaxy, rather than that, will be things behind the cluster because those rest sequence galaxies are the radius galaxy in the cluster. So then we can have a background sample. We just look at the shape of that background sample. Could you go down? Go down. Yeah, here is analysis of the magnitude and the magnitude error, but I would like to skip that. And here is the distribution of rest sequence galaxies and background galaxies. Rest sequence galaxies will have a concentration near the center of cluster, but background galaxies should be randomly distributed. This is like a check. And for lensing clusters, there's a lensing center. Usually that's the cluster center. So you would like to study the tangential ellipticity and the cross ellipticity. Tangential means it's perpendicular to the line between the cluster center and the galaxy. Cross is like 45-degree above that. And tangential ellipticity, we would expect on average, it has a positive value, but the cross ellipticity on average is 0 because of the lensing effect. And could you go down? And then go down more? Yeah, so we can make the histogram of those two ellipticities, and can you go down? From the top image, it's slight. We can sort of see the mean ellipticity in the tangential direction is slightly smaller than the cross, but it's hard to see. But if we find the difference between those two histograms, we clearly can see a dipole feature here that just telling us there's a difference between the two distributions, and that's the lensing signal. Could you go down? And go down more. So here, a typical plot people would make is this something called a profile. So here we are showing the mean ellipticity as a function of the radial distance. So along those blue points, along the um, tangential direction, clearly you can see a value above 0. But for those cross signs, for that direction, the mean ellipticity is constantly 0. So that's just telling us there's a lensing effect and the cross direction is close to 0. There's no significant systematics in our analysis. Okay, so that's it. Thank you. So now I just quickly go through some analysis through the portal. So earlier we show if you go to the RSP website, you will see there's an option for portal. So if you go into the portal, you will see some interface like this. We need to click this tab for catalogs because we want to check the catalogs. So if you go to the catalogs, you will see an interface like this. There are a lot of options. Basically, it's telling you whether you want to try some concert or like some other type of search, or what's available in the catalog, what rows columns are available, and then But here we want to use ADQL. It's basically some command line functions to do the search. Could you go to the next slide? So this query is very similar to what we showed before in TAP. So we want to get the coordinate, the magnitude, things like that, and make sure we select galaxies and make some cut on the magnitude and make some clone search. Could you go to the next slide? So after we give this ADQL language and actually run, it will take a while to make the search, and that's why we're just showing screenshot today. But after that, we will see an interface like this. It will show you a table of source of the galaxies, and then it will also show you some Higgs pixel images. But we need some cut to refine the figure. So click that filter. Could you go to the next slide? We just add some filter on the radial offset. So for example, 0.03 degree, then you will see the galaxies they're selected, those images of galaxies. And then you will also see the data points, how they're distributed on the sky in our deck. Those are the result of this cone search with this radial cut. Could you go down, go to the next slide? So there are options to try other type of plots. We show the scatter plot, but we can also make like histogram or heat map. But heat map, it requires a lot of data points. So if there's no enough points, then we cannot make that. We just want to make another scatter plot. Can you go down? So that's the G band versus the G minus R band magnitude. So then you can see the plot in the middle. So that's the red sequence. So that's similar to the previous notebook example. We can see the red sequence from this plot. Could you go to the next slide? If we click the gear and say we want to make some new plot, we can make a histogram. So that's the histogram for G band. And also we have this option to overplot. We can overplot some histogram. So for example, here we want to also show R band histogram at the overplot for the G band. So we can just use this overplot and show another histogram. Could you go to the next one? Yeah, so then in this result, if you look at the right part of the interface, you can see there are two histograms. One is for G band, one is for R band. So the portal is a very useful tool to visualize the data, and it provides a lot of useful tools to help you understand how the data looks like. Yeah, so that's it.
Thank you. I think we have some time for questions or comments. Checking the chat. Okay, I guess things were addressed. Nacho.
Yes, thanks very much for this overview. At the very beginning, I think it was you, Andres. You showed that shears would not be available as from the cell-based coads, DP1. But I guess object catalogs do include this HSM measurement, right? So it's not that there's no shape measurements. It's just that the specific ones coming from the cell-based coad process, it's only going to come later, but there'll be shape measurements anyway, right?
Yes. Thank you for
Yes.
the clarification. Yeah.
Yeah,
Okay.
I think the answer is yes.
So yeah, HSM is the one that Shenming was using in his example, but yeah, it will be available in that. But
And
not
later on, I guess this maybe it's a longer conversation, but are they going to coexist in later? That's what I'm seeing at the table, but I wasn't sure about that from someone. I don't know. So there will be, let's say, regular coad images and catalogs, and then coexisting with cell-based coads images and catalogs at some point?
I think
I
the answer is probably yes.
Yes, okay.
yeah.
But I guess there's also a lot of discussion on this. So things may change in the future.
Sure.
Yeah, and a lot of this discussion is also happening within the desk, and in the most recent science collaboration, there was a lot of discussion regarding this particular point. Yeah, thank you for the question. Tom asks in the chat if these slides will be available. Yes, please check online in the community forum post. The recording will be available as well as the slides. And everybody's welcome to follow up with questions in community, since we don't have a lot of time here, but we still have a few minutes if people want to ask anything else or have any other comments. And if not, we can finish here. And if you think of something, of course, let us know, as I mentioned. But thank you so much for coming and attending. And I hope you can come to the next Rubin assemblies about the other topics, design topics for the LSST. So yeah, okay. Thank you so much. And
Thank you.
have a great day.